Sorry, I lost my mic there for a second. Can you all see my screen and
Yes,
hear
we
me?
can. Yes.
Super, super.
And I'll give you
Okay.
a heads up with 5 minutes.
Okay, great. Thank you so much. And thank you so much for having me. I'm so excited to be here. My name is Emily Cunningham, and I am a Flatiron Research Fellow at the CCA. I'm calling in from Brooklyn tonight. It's evening, my time. And I'm so thrilled to be able to participate in this meeting. It's so difficult when we can't travel, but it's really wonderful to have the opportunity to share my work out in this community. I'm really, really grateful for the opportunity. So thank you so much. So today I'm going to be telling you about some work ongoing with both my own work and also some work from some students who are working with me. And while the focus of my talk is work on the simulations, I hope to convince you that this work is really motivated by observations and in particular spectroscopic surveys and using simulations in order to better understand our data and better understand the questions we should be asking of our data. Okay, so Sven already gave a fantastic introduction to the fact that we have these amazing data sets, including Gala and of course Gaia. This is the beautiful image of the Milky Way from Gaia. And we know in the lambda CDM paradigm of hierarchical galactic evolution, the Milky Way assembled its dark matter halo over cosmic time through the accretion of dwarf galaxies, smaller dark matter halos, some of which contain dwarf galaxies. And the remnants of these dwarf galaxies make up our stellar halo. And so a goal of many stellar halo studies is to use halo stars and trace back the Milky Way's accretion history and address the question of how and when the Milky Way assembled its mass. And while, with spectroscopic surveys and Gaia, there have been numerous substructures discovered, and we'll hear many exciting talks about that over the next few days. It's also a challenge to go from identifying substructure, to making quantitative inferences about the Milky Way's assembly history. In particular, these contributions from these low mass galaxies that are potentially extremely interesting, low mass, high red galaxies that formed at high redshift that haven't survived to present day, that we can observe in the field directly because they're so faint in the field. And yet we have the opportunity to study these systems star by star within the Milky Way galaxy if we can find them. But of course, they don't contribute very much by number, and locally they're bound to be phase mixed. So we have to rely on chemical abundances, in particular in the inner halo, to identify contributions to the overall halo from these systems. So I'm particularly interested in, one, how do we use the stellar halo to make quantitative inferences about the assembly history? And two, how can we identify or quantify the contribution from the remains of these high redshift galaxies that contributed, low mass, high redshift galaxies that are very difficult to find? So in order to address these questions, I turn to the simulations. So I'm showing you here a beautiful movie of one of the halos from the Latte suite of Fire 2 zoom-in hydrodynamical cosmological simulations. This suite was first introduced in Andrew Wetzel, and these simulations provide an amazing test bed for exploring many phenomena within galaxy formation, but my particular interest is different analysis procedures and understanding when we make certain choices in our analysis, how do we then learn, what are we really learning from these different analysis procedures? So I like to explore new methodology within the context of simulations, motivated by what methodology we should be using in our data and how we can maximize the impact and learn as much as we can from these amazing data sets that we have available online. So the goal of my talk today is to tell you in particular about a method for estimating the parameters of the Milky Way's assembly history using chemical abundances. And so to motivate this method, I'm first going to show you these images here, which are showing you the formation histories of two of the Latte galaxies. And when I say the formation history, what I actually mean is that I'm showing you a 2D histogram of the formation time of every star particle in a simulation. So I'm showing you one simulation on the left, another simulation on the right, as a function of its formation distance. So here you see these bright streaks on the bottom of the panels in this figure. These are stars that are forming in the disks of these simulations. They have low formation distance because they're forming in the inner regions or the near to the disk of the galaxy, in the disk of the galaxy. In contrast, these streaks out at higher distances correspond to stars forming in dwarf galaxies. And some of these dwarf galaxies survive until present day. So we can see a star forming dwarf here in the simulation M12M that is still forming stars at present day in the simulation. But we also see stars that are stars that form in dwarf galaxies and then interact with the disk and become disrupted. So in M12R, we see these thick streaks. That's indicating a lot of star formation. So these are massive accretion events that interact with the galaxy at late times in the simulation. So this is recent massive accretion. Whereas in contrast, if we look at M12M, we see we have these bright streaks that are interacting with the disk at early times. So M12M's halo is dominated by early accretion events. And one of the observational signatures of these different formation histories can be clearly seen in the chemical abundance ratio distribution, which I'm going to abbreviate as CARDS. And Sven gave a great introduction to a number of different distributions that one could look at in terms of elemental abundance space. But for me, for the purposes of this talk, and what I have access to with these simulations, I'm going to focus on magnesium to iron versus iron over hydrogen. And we can immediately see when we compare these two abundance distributions from these halos that have these very different formation histories is that we have very different, visibly different chemical abundance distributions when we compare these two halos. So for example, M12R's abundance distribution extends to higher metallicity and relatively lower alpha abundances. And this is consistent with the fact that it has experienced massive late time accretion. So there's plenty of time for these dwarfs to enrich through type 1a supernova. Whereas in contrast, M12M has higher density at lower metallicities and higher alpha, consistent with the idea that it is dominated by early accretion where there hasn't been a lot of time for enrichment through type 1a supernovae. Okay, so we can see with our eyeballs that we have these very different abundance distributions and that this is clearly linked to the formation histories of galaxies. But the question is, how do we then go from this to making quantitative inferences? So that's what I'm going to show you in today's talk, is a method for going from the chemical abundance ratio distribution using chemistry alone in this context in order to infer the parameters of the halo progenitors. So specifically, I'm interested in the mass spectrum of accreted dwarfs and when mass was accreted as a function of time in these halos. So to do this, I'm building off of a method that was first presented in an amazing paper from Dwayne Lee, who was a graduate student of Katherine Johnston's at Columbia. And this is called the CARDS method, that's what they call it. And the idea behind this approach is that it's an empirical approach where you can model the full abundance distribution of your halo as a linear combination of template abundance distributions for halo progenitors that have different properties. So there's a ton going on in this plot. I'm going to hide most of it from you for now. But first, just to orient ourselves, when I'm talking about halo progenitors of different properties, I mean first stellar mass. So in this grid of templates that I'm showing, stellar mass is increasing from top to bottom. So we have lower mass accretion events in the top row and higher mass accretion events in the bottom row. And then I've also created these templates as a function of progenitor quenching time, going from left to right. So, in the left-hand side, there are these are templates for halo progenitors that quench relatively early on. And on the right-hand side, there are templates for halo progenitors that have very extended star formation histories. So if we look in the top right corner, top left corner, we have a template. We can zoom in on this template, and this is a template abundance distribution for a relatively low mass, which to me means 10 to the 6. I know that is not low mass to everyone on the call, but this is the best I can do in the simulations for resolving the abundance distributions. We have a template for a relatively low mass halo progenitor that quenched relatively early in the simulation, so within the first 2 gigayears of the simulation. In contrast, we can look at a abundance distribution for a very late time accretion event that quenched very late and is relatively high mass, so 10 to the 8.5 to 10 to the 9. And we can see, in contrast to the previous slide, this abundance distribution is extended to higher metallicities, turns over, and magnesium versus iron, just as we expect from our understanding of chemical evolution. Okay, so the idea behind this technique is that you can take your overall halo abundance distribution and simply write it down as a linear combination of each of these different abundance distribution templates. And this is, just a linear model where you can use whatever version you want to solve for these coefficients. And these coefficients then correspond to the fraction of mass in the halo accreted from satellites with a given stellar mass and a given quenching time, in theory. So we'll get to the caveats. But so this is the technique that was first presented by Duane Lee in 2015 with Katherine Johnston. However, at the time, from the simulation side, they only really were working with Bullock and Johnston simulations, which are n-body and therefore have prescriptive abundances. And so this is the first time that this has been looked at in a cosmological simulation. And I want to pause and take a moment to acknowledge the fact that this work, as well as all other projects I've worked on in FIRE, really relies on the work from Nand Nithin Faisal, who is an outstanding graduate student from the University of Pennsylvania, working with Robin Sanderson. So Nand just wrote an excellent paper on stellar streams in the Latte simulations. And he actually made his catalog of streams publicly available. So you can Google him, check out his catalog to have a look at the streams in the simulations and check out his paper. But I owe Nand a great debt of gratitude because I used his catalog to create the templates for this work. So I've alluded to this a little bit already, but the real question I want to get at in this talk is how well this technique works in a cosmological simulation. And so the fundamental assumption in this technique is that if you have the stellar mass of a halo progenitor, and you have the amount of time that that progenitor took to form that stellar mass, can you then get a good prediction for its abundance distribution using an empirical template set? And what are the limitations of this technique? So here we have the opportunity to really explore these questions in detail because we're working in a cosmological simulation, which includes all kinds of exciting complications like dwarf-dwarf interactions, live disks and halos, all kinds of fun stuff, and self-consistent chemical enrichment. Okay, so does this work? The answer is sometimes, and I'm going to start positively. So this is my favorite Latte simulation. This is M12F. And what I'm showing you here on the left-hand panel is the abundance distribution from the halo. So this is the real data in this case. In the middle panel, I'm showing you the abundance distribution that we derive using our template set that we created for these simulations, using dwarf galaxies in this case. And you can immediately tell that our model distribution is a good match to the abundance distribution of the halo. We can quantify this using the residuals. We see the residuals are very low, and we're getting a reasonable prediction for the abundance distribution using our templates. But what about the properties of the progenitors? So here I'm showing you on the left-hand side the mass spectrum of accreted dwarfs, so the fraction of mass accreted as a function of the mass of the progenitor, where the true values from the simulation are in gray. And the results from our different template sets, so ask me about that at the end if you're interested, are shown as the colored points. And we can see that really for the mass spectrum, we're recovering this with very surprising accuracy, given, I can't emphasize this enough, that there is no physics in this model. This is really just a starting off point. We're only working with the chemical abundances and the empirical template set. So I'm showing you the residuals on the bottom, and you can see they're extremely low. On the right-hand side, I'm showing the fraction of mass accreted cumulatively as a function of progenitor quenching time. And you can see the residuals are a little worse, but again, really not that bad given that we didn't include any prior information in this model. And fortunately, M12F is not a unique success. For 4 out of our 7 Latte simulations, we can recover the mass spectrum of accreted dwarfs to precision of less than 10% or better, which is pretty, to my mind, I considered that a success. That was better than I thought it was going to go. And so this is, very encouraging. However, there are also caveats. So this is my failure story. I always say that's not my failure. It's the failure of the method on the simulations. So here I'm showing you the results for M12C. We're on the left-hand side, I'm showing you the abundance distribution for M12C, and you might immediately notice that it looks a little odd. It's got this big bright spot here at a metallicity of minus 1.1 and an alpha or magnesium of about 0.25. And when we compare the model from the template sets, we can immediately see that it doesn't look like the halo. It's not a good fit to data. We can quantify this with the residuals, that this template set is not producing a reasonable or a good model for the underlying abundance distribution. And so, unsurprisingly, when we try and infer the assembly history, so both the mass spectrum and the mass accreted as a function of quenching time, we're not getting precise inferences. However, this is not all bad news, because of course it's very interesting that we have this abundance distribution that's not well represented by our templates. So this is signaling that something interesting is going on and something anomalous is going on in this halo progenitor. But the other thing that's reassuring is that our first clue that our, thank you. Our first clue that our inferences are not going to be good is the fact that we have these high residuals, that we have a poor fit to the data. So this is really useful to know going in, and is also, potentially useful for model comparison if you wanted to create multiple template sets. The residuals are indicative of the quality of the inferences. So I'm showing you that here, where on the x-axis, I'm showing you the dispersion of the residuals of the abundance distribution models. So that's the dispersion of these residuals here. And so M12C has these very high residuals, and it's shown here in the orange points. And in the top panel, I'm showing how precisely we're inferring the mass spectrum. And the lower panel, I'm showing how precisely we're inferring the mass accreted as a function of the quenching time of the progenitor. And we have high residuals and poor precision for M12C. But we of course have M12F, which is shown here by the green points, where we have low residuals and high precision in the inferences for our assembly history. So to briefly summarize this study, we've heard this already in the first talk, and I'm sure we'll hear about this throughout the next 3 days, but the chemical abundance distribution of the halo is rich with information about the formation history of the galaxy. And in particular, in this talk, we focused on modeling this distribution as a linear combination of empirical templates. And we've shown that this has some success in 4 out of our 7 simulations, in fact, remarkable success. And to my mind, this is really a starting off point for a more complex model where you can incorporate additional information, or you could ultimately incorporate dynamics to really make these quantitative inferences that we're seeking about contributions to the halo from different kinds of galaxies. However, if your template set is not representative of your halo progenitors, you're not going to make the right inferences. But this is a signal that something interesting is going on, and that this progenitor warrants further study, and that our assumptions that we've made an assumption that is not accurate. Okay, so in my last few minutes, this first part of the talk was the majority of this talk about this study is really focused on what we can do with chemical abundances alone. But I want to take a moment to look to the future, and I want to highlight some work that's being led by an amazing graduate student, Danny Horta, who maybe some of you have met because he's in Australia. He's a graduate student at Liverpool who's been collaborating with me on a project in the simulation to study the remains and the observable properties of accretion events in the fire simulation, with an emphasis on early accretion events in the mass range of 10 to the 7 to 10 to the 9. And this great plot that Danny has made is showing the median galactocentric radius of debris from halo progenitors as a function of their infall time, and color-coded by stellar mass, where the shape of the point is indicating the dynamical state of the debris. So circles are phase mixed, triangles are coherent structures or streams, and diamonds are dwarfs. And so if we look at this plot with the volume of Gaia and 4-meter class spectroscopic surveys in mind, we can see when we look down here in the inner halo that in the simulations, everything is phase mixed. We also see these big, massive events that around 10 gigayears that are, this is very consistent with Gaia and Enceladus sausage dominating all of our Gaia samples. We see these massive early events in the simulations as well. And in this regime, because everything here is phase mixed, you would want to rely on chemistry to really disentangle these populations. But if we think ahead a little bit and are willing to look out into farther distances in the halo, where we'll be able to see with LSST and W first in kinematics, I want to highlight this sort of section of the image at the top right, where we can see that there are a number of relatively low mass systems that are still existing as coherent streams at really large distances out into the halo. So we're not limited to the inner halo in order to identify these sort of early, very interesting lower mass galaxies that formed at high redshift. but there's still a lot of discovery potential in the outer galaxy for a number of different reasons. But here I want to focus on the lower mass systems that survive, that were disrupted at early times and form these streams at really large distances in the halo. And so, and critically, these will also be resolvable in kinematics and not in chemistry alone, because we still see that they're coherent streams because the dynamical times are so long way out there in the halo. And of course, spectroscopy will have a critical role in characterizing these events. So here, Danny is showing the mean magnesium over iron versus iron for his catalog of progenitors. And on the left, it's color-coded by stellar mass. And on the right, it's color-coded by infall time. So we can see mass metallicity very beautifully in the left-hand panel. And then we can see, of course, on the right-hand side, the fact that at fixed metallicity or fixed stellar mass, later accretion events will have lower alpha abundances than their earlier counterparts. So very exciting future for studying, the remains of these disrupted dwarf galaxies. And it's been really, please look out for Danny's paper. I've been working very hard on it, and it's an outstanding paper. So I will leave my conclusions up and take questions. Thank you so much.
Thank you, Emily. That was great. Do we have questions for Emily? So it looks like Evan Kirby.
Hi, Emily. Great talk.
Hi, Evan. Thank you.
Hi. I had a question about the card, specifically these sort of eigenvectors that you were using, the templates for the magnesium over iron versus iron.
Yeah.
Correct me if I'm wrong, but some of the lower mass ones didn't really look like how actual dwarf galaxies look. Like, for example, the 10 to the 6 mass one that you showed, like the quintessential 10 to the 6 solar mass dwarf galaxy sculptor. And the sort of card that you showed was much more metal poor than the MDF of sculptor. And I was just wondering, you made a comment about how the templates may not exactly reflect the true progenitors, but I was just struck by how metal poor some of the lower mass dwarf galaxies looked in here. And I was just wondering if you thought much about that.
Oh, yes. Thank you so much for raising that point. And I'm so glad you spotted that. And I meant to make this point more strongly, and I didn't. These are templates for Latte halo progenitors, not real progenitors. And that's because of this point that you just raised, which is that the dwarfs in fire and the halo progenitors are too metal poor relative to the observations. And this is something that was not initially appreciated, but is appreciated in particular in Ivana Scala's paper, excellent paper on comparing the abundances. So you're absolutely right that they're too metal poor. They have these weird shapes. So for example, there's basically an alpha cap at fixed iron, and this is a result of the initialization of the star particles. They are all initialized with a -4 metallicity. So these are not intended to be applied to the observations without considerable care or needing to make a lot of calibrations or assumptions. So yes, thank you for raising that, because that's a really important point, that these are templates for the simulations to be applied to the simulations. And hopefully the idea is that with dwarf galaxy observations, we could create empirical observational templates.
So it's not the main thrust of the work to construct simulations that look more like the actual dwarfs. It's more to use observational templates to match observational data.
Right. But there is actually going to be a very exciting opportunity to do what you just described by tuning the simulations to look more like the observations with the new age tracing functionality that's coming out in Fire, which I can talk about if people are interested. But we're going to be able to essentially tune in post-processing, trying different yields and trying different chemical enrichment models in post-processing in order to match the observations more accurately in the new generation of Fire.
Got it. Thank you. Thank you, Emily.
Thanks, Evan.
Do we have other questions for Emily? So I'll go ahead and ask one. So on this, it's actually on the slide for the cards. You only have a few, particularly for the high mass ends templates. So that might be one of the reasons, particularly like that one galaxy kind of didn't work out so well. How do you how would you go about generating more templates? Are you basically restricted to what you have in Fire, or how can you kind of fill in the missing coverage area?
Yeah, great question. So you've raised a really interesting point, which is especially at the massive end, even when we have halo progenitors that have similar quenching times and stellar masses, they themselves can have diverse abundance distributions. And this is a result of their different star formation histories. So actually, interestingly, this M12C oddball accretion event is a result of, you can see it has a very bursty star formation history compared to the other accretion events of its stellar mass and quenching time. But also, fascinatingly, this big burst of star formation coincides with its first pericentric passage. So it experiences a pericentric passage-induced starburst and forms too many stars too fast to follow the standard track of chemical enrichment. So at the moment, I could try to seek out more templates, or I also think it's going to be exciting to play with combining observational data sets and simulated data sets, as I just mentioned, by tuning the simulations to match the observations. There are theoretically more abundance distributions that I could include with Fire. I stuck with the limited catalog for the purposes of this first, proof of concept. But you're right that is testing the fundamental assumption of the technique, that you cannot always predict with perfect accuracy what the abundance distribution is going to look like given mass and quenching time. Did that address your question?
Yes, thanks. Any other last minute questions for Emily? All right, if any come up, please feel free to use the chat or post on the Slack.